So today we'll be covering another section in Thinkwell Calculus. We're going to go to an introduction to derivatives and click on finding instantaneous velocity. So we'll be working the problems out through this section. So we'll begin with our first problem here. The provided graph shows the position function of an automobile based upon the shape of the graph, at which point was the automobile moving the fastest. Alright, so as we covered in our previous video, we know that velocity equals line tangent and the slope. So basically the concept we have to understand is where the velocity is fastest. So the faster the velocity, the steeper the slope. So basically we're going to go through these points and look for where the slope is the steepest. We'll begin with F. We see that it is almost horizontal here, so that can't be it. At E, it is horizontal, so that can't be it. At D, we see that the slope is somewhat steep. At C, not quite steep. At B, it is very steep. And at A, it is somewhat steep. So out of all these options, we can see that B has the steepest slope. So the answer is point B. And we can verify that by going to our question. And we see that point B has the fastest velocity. Moving on to our next problem, we'll go to this. As the car brakes to a stop, its position is given by the function xt equals 20t minus 2t squared, where t is the time in seconds and xt gives the car's position in feet. What is the car's instantaneous velocity when t equals 2? Basically, we can very easily solve this using the basic derivative rule. So we have xt, which is 20t minus 2t squared. This is a little more advanced for students who are going according to Thinkwell, but this is the easiest way to do this problem. So x prime t, which is the way to write a derivative, would be 20 minus 4t. Once we have that, we plug in 2. So now we have x prime t equals 20 minus 8 equals 12. And that is our answer right there, 12. That is the car's instantaneous velocity. So instantaneous velocity when t equals 2, 12. And this could be in meters per second, feet per second, just depends on what the problem is given in. And if we look up here at our answer choice, we can see that the answer is 12 feet per second. And we can move on to our next problem. So moving on to our next problem is this. The provided graph shows the position function of an automobile. Somewhere on the trip, the automobile had a flat and the driver pulled over to the side of the road. What time on the graph is most likely time that the driver stopped? Alright, we did a problem like this in another video. Again, we know that velocity equals line tangent, or also known as the slope. Basically, when the velocity equals 0, the slope equals 0. And in order to have a 0 slope, we must have a horizontal tangent line. So that is the key thing to remember, horizontal tangent line. So again, we just go through these and we see where the line is horizontal. At F, we see that it's not horizontal. At E, we see that we have a horizontal line. Just to make sure, we'll check the other spots. D has a steep line tangent. C has a somewhat horizontal, but not quite. B is steep, and A is somewhat steep. So the correct answer would be point E. And that is our answer to this problem. We can check this in our Thinkwell, and we can see that time E, or point E, is the correct answer. So, we'll move on to another problem. The position of an object moving in a straight line is described by the position function pt. Which of the following expressions is equal to the instantaneous velocity of the object at t equals 3? In order to understand this problem, we'll be approaching limits. And limits, we have a special theorem that is given to us by Professor Berger, but of those who are just doing these problems, the theorem is simply as the limit of A approaches 0, we have, as the limit of delta t approaches 0, we have P of A plus delta t minus P of A over delta t. And this is just an applied simple calculus theorem. And so now we simply just plug in t equals 3 for where we have A. So basically we're going to do P of 3 plus delta t, and then we're going to do minus P of 3, and then we're going to do that over delta t. And that is our answer right there. And we can check this again in our solutions. We can see P of 3 plus delta t minus P of 3 over delta t. And the part that we forgot here, and this is my mistake, I apologize, is as the limit of delta t approaches 0. And this is an extremely important part of the problem. But basically, that is our answer right there. So moving on to our next problem, which is quite difficult. A marathon runner's distance from starting point is given by a piecewise function, and you can see the piecewise function, where d is measured in yards and t is in seconds. What is the runner's instantaneous velocity at t equals 4 seconds? In order to do this problem, we must first understand what they are asking. So basically, what are we looking for? Well, we need to find the velocity when, so velocity, and this is instantaneous velocity when t equals 4. So that is our key part right there, when t equals 4. We also have to, so this is our number 1. This is what we are finding. Number 2, what we're given is a piecewise function, as it says here, piecewise function. We're only concerned with the first portion of this piecewise, and that is 50 t over 8 squared, where t is less than or equal to 8. That is the only part we're concerned with, since our t equals 4, which is less than or equal to 8. Alright, then we need to remember our expression from the previous problem, which is p of a plus delta t minus p of a over delta t. So basically, our a in this time is t. We also need to understand that, so let's just plug in our values now. So let's plug in our values. So number 4. And I know this is a bit confusing, but just bear through. Here we go. So we have to use that right there. Alright, so we know, okay, so we're going to combine these two parts right here. We're going to combine this expression into this theorem that is given. So we're going to combine this expression right here into this theorem. So first step is we're going to take the 50 and put it aside, because that has nothing to do with our unknown values. So we have our 50. Inside we have our t plus delta t over 8. Alright, so what we're basically doing is taking this part, t over 8 squared, and we're putting it right in here. So t plus delta t plus delta t over 8. And now what are we going to do? We're going to square it. Alright, minus. So now we're going to take the minus portion. So we're going to take this portion right here, the minus, and plug in our value again. So minus 50 t over 8. And again, squared. Then we're going to put all of that. As we see here, all of this is over delta t. So we're going to take all of this and put it over delta t. Alright, so we have that part. We're not quite done. Now we have to take this and we have to expand it. We're going to use FOIL. Many of you have heard of FOIL. It is used in high school a lot. FOIL or FLIO, where we take the inner terms. So right here, we take the inner terms and we're going to square. So right now, we're going to do step number 5. We're going to do 50 times t plus delta t over 8 times t plus delta t over 8 minus 50 t squared, well, 50 t over 8 times t over 8. And basically what we're going to do is FOIL all of this out. So multiply the inner term, the t times the t, and then so t times t, and then delta t plus times t plus delta t times t, and delta t times delta t. So very confusing. And then the 8s, multiply the 8s together. Here we're going to do t squared over 64. What we finally end up with is, and let me expand one more time. What we're going to end up with is 50 t squared plus 100 t delta t plus 50 delta t squared minus 50 t squared over 64. And I also forgot this part, which is over 64 over delta t. Alright, so almost done here. we have this main part. As we see here, we have a negative 52